Welcome back to Very Ordinary Differential Equations. In this lecture, we begin our study of second-order linear equations with the concept of a fundamental set of solutions. So what is a second-order linear differential equation? Well, it's one that can be written in the following form. Y double prime plus p of xy prime plus q of xy equals f of x. Now this is very similar to how we defined a linear first-order equation where we had y prime plus p of xy equals f of x. But because we're a second-order equation, we've got a second derivative in there, we've got an extra term. If f of x, the forcing function, the function that is not being multiplied by y or y prime, if that forcing function is constantly zero, the equation is called homogeneous. Then we just have y double prime plus p of xy prime plus q of xy equals 0. If that forcing function is sometimes non-zero, it's called inhomogeneous or non-homogeneous. So let's take a moment to recall how we worked with homogeneous first-order linear equations. Now, if we had a first-order linear homogeneous equation, y prime plus p of xy equals 0, the function y equals 0 is always a trivial solution, and we always relied on the fact that if we found one non-trivial solution, then all solutions must be some scalar multiple of the non-trivial solution that we found. Is there a similar simplification that holds for second-order homogeneous linear equations? Well, we have to do a bit of linear algebra to justify a few things. The answer, fortunately, however, is yes, there is a similar simplification. For the homogeneous linear second-order differential equation in our standard form, linear algebra can help justify that the set of solutions defined on some interval where all of the coefficient functions p and q are continuous, the set of solutions is two-dimensional. If we can find two solutions that are linearly independent, then their span forms the set of all possible solutions. Don't worry if this linear algebra terminology is unfamiliar. We're really not delving into the theory here. We're just trying to justify the following statement. If we can find two solutions, y1 and y2, that are linearly independent, then all possible solutions must be some multiple of y1 plus some other multiple of y2. So c1 and c2 are different constants. They might be the same constant, but presumably they're usually going to be different. Now let's introduce the notion of a fundamental set of solutions. Suppose you have a homogeneous differential equations and you have a set of solutions, y1 through yn. For our purposes, for now at least, n is just 2. You only need 2 solutions. But in general, perhaps you have n different solutions that form a linearly independent set of functions. Also, any possible solution is a linear combination of the functions you have. In other words, a sum of constants times the functions that you have. Then this set forms a basis of the space of solutions. This is linear algebra terminology. For us, we're going to call this a fundamental set of solutions. In linear algebra terminology, a fundamental set of solutions is just a basis of the solution space. In second-order differential equations, we modify this and we just say any two linearly independent solutions comprise a fundamental set of solutions. Linear algebra helps justify that assuming all the functions involved are continuous on some interval, then the set of solutions is two-dimensional, so all we need are two linearly independent elements to form a basis. So any two linearly independent solutions make up a fundamental set of solutions. So how am I going to establish that two functions are linearly independent? For the sake of argument, let's suppose I happen to have found two different solutions, y1 and y2, to our second-order linear differential equation in its standard form. I need to check that they're linearly independent. If they are, then I've actually found a basis for the solution space. In other words, I have found a fundamental set of solutions. Now, two functions are linearly independent on an interval if and only if I cannot possibly find a constant k so that y1 is equal to k times y2 on that interval. This is usually a pretty easy condition to check. We just have to verify that the two solutions we have are not multiples of one another. If one solution cannot be expressed as a multiple of the other, then you have found two independent solutions. In other words, you found a fundamental set of solutions. Once you have a fundamental set of solutions, you know that all possible solutions can be written as a multiple of y1 plus a multiple of y2. These c1 and c2, again, can be arbitrary constants. They might be equal to one another, but they might not be. They're just two real numbers. So if we're only dealing with two functions, y1 and y2, linear independence is pretty easy to check. But looking ahead, we may be interested in solving higher order differential equations, in which case the linear independence of a solution set can be a bit trickier to establish. In general, suppose you have a collection of functions, y1 through yn. They're all defined on some specific interval. The Wronskian of these functions is the determinant of an n by n matrix in which the first row is the functions, the second row is the first derivative, the third row is the second derivative, and so forth. So what we have is a giant n by n matrix. Notice that this first row is just the functions y1. The second row is going to be the first derivative of all of them, then the second derivative, all the way up to the n minus first derivative. Okay, if I started off with the function and then the first derivative, if I want to have n rows, I'm going to end with the n minus first derivative. So the Wronskian says, make the matrix of functions, first derivatives, second derivatives, and so forth, and then take the determinant of this giant matrix. What does linear independence have to do with this matrix? And again, we're not really delving into the linear algebra theory here, we're just kind of stating results. The functions, y1 through yn, are linearly independent on an interval if and only if the Wronskian is not constantly zero on that interval. So we're really not going to develop a formal proof, but what generally ends up being shown is the following. The Wronskian is either constantly zero or never zero. So whatever interval your functions all exist on, this Wronskian either is always zero or never zero. The Wronskian is going to be some function. Therefore, if it's not constantly zero, if there is any point on the interval where it's not zero, then it must never be zero. And when the determinant of a square matrix is non-zero, the columns are linearly independent. So if the Wronskian is not constantly zero, then for every value in the interval, the columns of that matrix we formed must be linearly independent. The columns was just a list of derivatives. The first column was y1, y1 prime, y1 double prime, and so forth. The second column was y2, y2 prime, and so forth. Okay, so the columns are just lists of derivatives. If those columns are linearly independent, it follows that the first entry in them are linearly independent. And this isn't in general true for matrices, but it's true for this specific one. And the first entry of every column was just the functions y1 through yn. Now, in a two-dimensional problem, the Wronskian's a bit simpler to work with. So we have two functions, y1 and y2. I'm going to make those my first row and their derivatives the second row. And I just need to compute the determinant of this 2 by 2 matrix. The first row is the function y1, y2. The second row are the derivatives y1 prime, y2 prime. Now, a determinant of a 2 by 2 matrix is pretty quick to compute. We just take the difference of the diagonals, y1, y2 prime minus y1 prime, y2. So our two solutions form a fundamental set of solutions on an interval if and only if this determinant is non-zero at any single point in the interval. If it's not zero at a single point, it will never be zero. So if we can ever verify that y1, y2 prime is not equal to y1 prime, y2 for any single point on the interval that we're trying to find our solutions on, then we will have shown that these two solutions are linearly independent and therefore form a fundamental set of solutions. So let's take a look at an example. y1 is e to the x and y2 is e to the minus x. We want to show they form a fundamental set of solutions to the equation y double prime equals y. Well, we're going to rewrite this in our standard form, y double prime minus y equals 0. Let's verify that both of our functions do actually solve the differential equation. That's actually not a very tough problem. y1 double prime is just the same as y1, and y2 double prime is also the same as y2. Now, y1 prime is the same as y1, and that's not true for y2. y2 prime is negative e to the minus x, but if I take a second derivative, I'm going to get back to y2. So y1 and y2 are, in fact, both solutions. They're defined and continuous at all real numbers, so the interval in question is all real numbers. So if we can verify that the Wronskian of these two functions at any particular real number is not zero, then we'll conclude that it is never zero, and then we will conclude that we have, in fact, found a fundamental set of solutions. So we have to check if the Wronskian is ever 0. And the Wronskian for two functions is just this difference y1, y2 prime minus y1 prime, y2. y1 was just e to the x, y2 prime is negative e to the negative x, and similarly y1 prime is e to the x and y2 is e to the negative x. This is exactly negative 2. Are there any real numbers for which negative 2 is 0? No, of course not. Negative 2 is never equal to 0. Our Wronskian is quite transparently never 0. So since the Wronskian is never 0, the two functions are linearly independent. Since we have a second-order linear differential equation and we have two linearly independent solutions, we have in fact found a fundamental set of solutions from which we conclude the only possible solutions to the differential equation we started with, y double prime equals y, must be of the form some constant times e to the x plus some other constant times e to the minus x. Looking at a second example. y1 is sine x, y2 is cos x, and we are to show they form a fundamental set of solutions to the equation y double prime equals minus y, and then solve that differential equation under some initial conditions that y of 0 is 3 and y prime of 0 is 1. Now, as before, we should check that these two functions y1 and y2 are actually solutions to the equation y double prime equals minus y. Of course, two derivatives of sine bring you back to negative sine, and two derivatives of cosine bring you back to negative cosine. So, indeed, the two functions we were given are solutions to the differential equation we started with. But we should check that they're linearly independent. So we compute the Wronskian, y1, y2 prime minus y1 prime, y2. Okay, y2 prime is just negative sine x times sine x gives me a minus sine squared. y1 prime is cos x times a cos x gives me a cos squared. So I have negative sine squared minus cos squared x. I, of course, can factor out the minus sign, leaving behind a sine squared plus cos squared, or a 1. So the Wronskian of these two functions is a constant negative 1. Negative 1 is never 0, so our Wronskian is never 0. So our two functions are linearly independent, so we have a fundamental set of solutions. So we've now verified that sine x and cos x form a fundamental set of solutions to the differential equation in question. Therefore, we conclude that any possible solution is some linear combination of sine x and cos x. In other words, a multiple of sine x plus a multiple of cos x. In this case, y prime would be c1 times cos x minus c2 times sine x. I just differentiate y. Now we have some initial conditions that we can plug in. For the first one, if I let x equal 0, sine of 0 is 0, cos of 0 is 1. So on the right-hand side, by letting x equal 0, I'll just get c2. But we were given that y of 0 is 3, so c2 must equal 3. Similarly, in our second equation here, given that y prime of 0 is 1, this cosine is going to spit out a 1, while this sine is going to spit out a 0, and we immediately get that c1 must be 1. So therefore, we have found our constants c1 and c2, so the exact solution to our equation is 1 times the sine of x plus 3 times the cosine of x. As a third example, let's verify that y1 equals e to the 2x and y2 equals e to the minus 3x are both solutions to the linear, second-order, homogeneous differential equation y double prime plus y prime minus 6y equals 0. Once we've done that, solve the initial value problem at y of 0 equals 0, y prime of 0 equals 2. Well, we're just going to check solutions by computing first and second derivatives and plugging it into the differential equation. For y1, the first derivative is 2e to the 2x, and the second derivative is 4e to the 2x. Plugging it in, everything cancels, we get a 0, it is a solution. For y2, the first derivative is negative 3e to the minus 3x, and the second derivative is positive 9e to the minus 3x. We plug it in, everything cancels, we have a solution. So since we have two solutions, we should check that they are in fact linearly independent, and we do that by computing the Wronskian. y1, y2 prime minus y1 prime, y2. These derivatives have already been computed as part of checking that they were solutions. Note that e to the 2x times e to the minus 3x is just going to be e to the minus x, and altogether we have minus 5 of those. Minus 5e to the minus x is not constantly 0. It's actually never 0. On the set of all real numbers, e to the minus x is never 0. So on the set of all real numbers, the two solutions are linearly independent. Since we have found two linearly independent solutions to a linear second-order homogeneous differential equation, we conclude that any solution must be a linear combination of them. In other words, some constant times e to the 2x plus some constant times e to the minus 3x. So having determined that any solution to the differential equation must be of this form, we can start using our initial values to determine what those constants are. So plugging in 0, we compute y of 0 is given to be 0, so y of 0 is 0. On the other hand, if we let x equal 0, both of these exponentials are 1. So whatever the constants are, their sum must be 0. But if I take the derivative of y, I'll get 2 c1 e to the 2x minus 3 c2 e to the minus 3x. Plugging in 0 sets the exponentials to 1, but y prime of 0 was given to be 2. So 2c1 minus 3c2 must be 2. Now we just have to solve the following system. c1 plus c2 is 0, but 2c1 minus 3c2 is 2. And c1 and c2 are just constants. We solve it with c1 is 2/5 and c2 is negative 2/5. Techniques for solving such systems should have been covered in previous courses. We're not really going to get into it here. This should be something we're all capable of doing at this point. So having determined the general form of solutions and then specifically finding the two constants using our initial values, our exact solution to the differential equation with our given initial values must be 2/5 e to the 2x minus 2/5 e to the minus 3x. We can factor a 2 out of that numerator and present it like this. All right, so what have we done? A linear second-order differential equation is of the form y double prime plus p of xy prime plus q of xy equals f of x. When that forcing function f of x is just 0, the equation is called homogeneous, and that's actually all we looked at today. If we are looking at a homogeneous linear second-order equation, then all possible solutions are spanned by any two linearly independent solutions we can find, y1 and y2. We can check for linear independence of two functions using the Wronskian of two functions, y1, y2 prime minus y1 prime, y2. If that Wronskian is ever 0 on the interval of the solution, then it is always 0 and the solutions are not linearly independent. But if it is ever non-zero, then it's always not 0 and the solutions are linearly independent. If you have two linearly independent solutions, y1 and y2, then all possible solutions must be of the form some constant times y1 plus another constant times y2.